no need to have for uh, all the cases. Okay. Yeah. Yeah, so calculator will be there in the I think computer itself. So there is no issue. Yeah, yeah, yeah. Aha, okay. Okay, okay. Okay. Okay, okay. Yes, 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 yes. That's a standard form. And because nowadays the calculators are also very much programmable, so they don't want everyone to force to buy a particular brand of calculator. So then it will be difficult. So that's why I think they have implemented this online thing. Yeah. If you have also any other question, we'll discuss. Okay. And tomorrow also there will be session. So what I'll do, I'll have few problems for tomorrow also from this failure theories. I have not covering today failure theories because some portion is being covered in this week, some portion is being covered in the next week. So what I am thinking to take failure theories as one. So today I'll just finish off in the beams deflection basically. So we'll see in deflection and next time onwards, that is tomorrow, we'll do failure theories, and column is also there for tomorrow. So I think you have already seen the lectures are already out. I think. Yeah. Yeah, yeah, yeah. Yeah. So buckling is also there, and failure theory is also there, so that we can discuss tomorrow also. And if you have any doubt with respect to the assignment, all of you can ask today. Okay, we'll do that because I have few questions to discuss because it's already the superposition principle, the fictitious load method, also known as unit load method. These are like there is it's just to need to just to have more problems. As you solve more problems, you will understand more. That's all. But they are a repetitive kind of problem. There is nothing new in any problem. So if you have any doubts, any of you have any doubts with respect to assignment, also I'll just try to help you wherever I can possibly. Okay. Yeah. We'll start in few minutes. Okay. Yeah. Yeah. Yeah, so good evening all. Uh, Today in this session we'll discuss about the some of the concepts while for solving the deflection of beams. So in today's session we'll use the method of superposition and method of fictitious load, or also known as unit load method, unit load method, to solve some of the problems for deflection. I hope my screen is visible. I think my screen is visible. Yeah, thank you. So in today's session we'll discuss these two things, and this will be the kind of, in this basic course, the I would say that will be sufficient or enough for this level course for discussion on deflection. So although at higher level there are other courses, but basically in the background of mechanical engineering this is sufficient. However, in the background of civil engineering there could be more courses on deflection. So because when we sometime define something like, there is something called displacement based method and there is something called stress based method, and from them we go to the uh, we further go to the something called stiffness matrix and something called uh, uh, the inverse of stiffness matrix. So those concepts come. So then we graduate to the our FEM, basically finite element method, from there itself. So but that is very high level. So in this we'll just discuss the uh, deflection of beam using the uh, superposition principle and fictitious loss method. We'll see that today, but let's have a recap because it's been long time and the assignment of this one is being over. So we'll do a small recap also for this. So we had seen that the for finding the deflection, so we had d power 4 y by dx power 4 ei is equals to q. We saw that we had some equation like this, and we knew that if we integrate it, so if we get integrated, so we will get something called ei d cube y by dx cube is equals to qx plus c1, and then we further integrate it, so we'll get ei, and I'm saying here that ei, which is also known as flexural rigidity, is held constant, okay, because I am not integrating that, I'm keeping that outside the integration. That means constant rigidity is constant, okay. So d square y by dx square is equals to qx square by 2 plus c1x plus c2. Then we integrate it once more, integrate, so we get ei dy by dx is equals to qx cube by 6 plus c1x square by 2 plus c2x plus c3, and then we finally integrate to have the form ei y is equals to qx to the power 4 upon 24 plus c1x cube upon 6 plus c2x square by 2 plus c3x plus c4. So this is the final form we get after integration. Simple, nothing new. And we need boundary conditions. of the beam for finding the constants. Okay, in order to find these constants C1, C2, C3 and C4, we need boundary condition, and as you can see here, you need 4 boundary condition. Okay, so it depends now on the problem, how the problem is being posed, what kind of beam it is, if it is a cantilever beam, whether it is a hinge beam or a simply supported beam, it's a propped cantilever beam, what kind of beam it is. Based on that you can identify these boundary conditions. So I'll just lay out some simple boundary conditions. Okay, so boundary conditions for simple cases. Okay, so let's have a case like let's say our favorite cantilever. So what boundary condition we can use for cantilever? So what I will do, because I have written an equation in which Q is there, a uniformly applied load Q is there. So what I'll do, you have to use this only when you have a uniformly distributed load like this. Okay, however the boundary condition will always be same. Okay, but this equation we can use only in that case when the loading is like that, otherwise we can't. We have to write in terms of bending moment. Okay, if we have a point load or something similar, something different, so apart different from the uniformly distributed load, so we have to come up to this final equation of y in a different form. This equation of y will come up to in a different form. However, the boundary condition won't change. They depend on the geometry of the structure or the kind of the supports we use. So it doesn't matter on the loading. Okay, only the movement changes basically. So here let's see, this is A end and this is B end. So for A end we write that deflection y at A is 0. We know that at this end deflection and rotation both are 0. So we say y is 0 and we say dy by dx, which is the slope, also at A is 0. We put two things as 0 there. So now this is clear. So out of 4 we have defined 2, and then other is the bending moment. So at this point we know the bending moment is 0. Obviously, you know, if some load will come like this on this cantilever, it is going to deflect like this. So you can't say that deflection and slope are 0 at the point B. So what you can say that the moment M at point B is 0 and the shear force V at point A is 0. So these you can say, these are 0. Okay, so now let's move to our next case. So we have like some simply supported beam. So here a hinge, here a ruler. This is A, this is B. Okay, so the boundary conditions you can say. So as you know, this end won't deflect. Okay, but this will have a slope. So if your load will be there, it will reflect like this. So the deflection will be 0, but slope will be non-zero there. So you will say theta A, or which is also written as dy by dx at A 0. Correct. Similarly, we can write for theta B. Okay, at B end, because that is also a roller. So for that end, we can write our boundary conditions. Theta B will be dy by dx at B being 0. Oh, sorry, I am writing in the other way. I should have written non-zero. Sorry, non-zero, non-zero. I'll write that in another color. Sorry, is equals to dy by dx at B is non-zero. So what is zero? Deflection. Y at A is 0 and Y at B is 0. This is 0. Deflection is 0. Theta is not 0 there. So sometime in hurry we make that mistake, but we should remember that. Okay. And then what other conditions it have? So you know that the bending moment at hinge is 0. Okay, at any kind of hinge the bending moment is 0. So we can use that property. So we can say that the in bending moments I will say M at A will be 0 and M at B will be 0. Okay, so this we can point out. Similarly we can have one more case. So it is something like propped cantilever case. So it's a hinge here, it's a roller here. Okay, so what are the boundary conditions for this case? So you know that this is a hinge fixed support, this is a hinge support. So you know that what tall is 0 at fixed support. So the deflection Y at A is 0, deflection is 0. Then the slope also dy by dx at A is 0. Okay, then coming to the point B, we know that here at point B we know that deflection is 0. Again it's a ruler, so YB is 0. And another thing we know at this point is the slope is 0. Oh, sorry, the bending moment is 0. We know that slope is not 0 there. So slope, if I write dy by dx, B is non-zero, but the bending moment is 0 at B. Okay, so these are our 4 conditions which can use to find the constants in this case. So similarly we can have other different cases and we can assign different boundary conditions accordingly. Okay, and this how we solved the problem last class with for the this for this case of for the method called integration method or double integration method. Basically we'll integrate. So if we define the we define this y with respect to the bending moment, then this equation comes actually. So it is e d square y by dx square is equals to m. Okay, and from there we find the value of, then we integrate it twice and we find the value of 2 constants. There we need 2 only unknown boundary conditions, but here we are starting with q, so we need 4 boundary conditions. Okay, so that is there. Sorry, yeah. So now this is the recap for that. Now let's go what was the principle of superposition. Okay, so in principle of superposition what it says that for the case where there are certain restrictions on that also, you can't, it is not like that you can forever use the principle of superposition. There are few restrictions. Restrictions are such as when there is a non-linear response of material. So suppose there is a material where the response of the material is non-linear. Okay, by non-linear response what I mean sorry, by non-linear response what I mean is that the stress strain relation. Okay, so we have seen in our case that the stress and strain are related linearly. There is no square term in that. We have seen in Hooke's law. So when there is a non-linear relationship between the stress and strain, so in that case we can't use the principle of superposition. and that is why if you remember properly, that is why while discussing the uh, energy methods, okay, discussing basically the Castigliano theorem on energy methods, and specifically in fictitious load method, professor told that he put a caution that do not use the superposition principle. Okay, he put a caution there that do not use the superposition principle. Why he put that? Because the relationship between the complementary strain energy U and the relationship between the quantity M, which is bending moment, or suppose shear force V, or suppose axial load P. So the relationship between these two is not linear, it is non-linear. The relationship is non-linear. That's why we cannot use there the principle of superposition. Okay, so now what happens that so that is one scenario I told. Then there are some scenarios of like lack of fit problem. So lack of fit problems are problems in which the stresses are generated due to some unevenness of the members or the construction or the geometry. Okay, so those are called lack of fit problems. Like suppose if there is a there is a beam is there. Now that beam has to be casted for a specific length. So suppose the length should have been 5 meters. Okay, and it has to be kept in that length of 5 meter itself. Okay, you had a roller one side and a hinge on the other side. Now you cannot put your distance between the roller and hinge more than 5 meter. So what will happen? Your beam has to be compressed first to put it in a particular place. Okay, so basically in case of hinge you can't do that, because what will happen? Roller will move away. If you will do that, roller will move away. So because why it is happening? Because it's a determinate structure. So in determinate structure you cannot have stresses generated due to lack of fits. So when you see it, when you have a indeterminate structure, so suppose you have a fixed beam. I'll give a very short example. You have a fixed beam, suppose something, or I would say this area is there, some area like this, some region is there between these two fixed. Now I have to fit a plank. Okay, this is a plank. Okay, now this plank I have to fit here, because you can see this is plank is more than this one. That means if I have to fit, I have to make in a way I have to make this in a way so that it properly fits like this. Okay, so what I am doing, I am actually compressing it, then only I am able to fit it. Okay, and then I can say okay, it is behaving like a hinge fixed support. Okay, for this case, so as how I told, you have to compress this one to put it in here. So for this case what is happening, that due to this compression already the stresses are developed in the plant. Okay, due to this compression. So such problems where you have indeterminate structure specifically, and then you have a lack of fit problem or a thermal loading problem specifically in indeterminate structures, there also you can't apply the principle of superposition. Okay, you can't apply the principle of superposition. So that is, there has to be considered properly before going. Now what principle of superposition says that, so suppose you have a beam. Okay, so like this kind of thing, A is A, is B. Now I have been asked to find the deflection and slope of this beam at this distance L1, which is point C. I have been asked theta C and delta C. What is the deflection at theta? What is the slope at theta? So what I can do, so now this is my first loading suppose. and this is my second loading. So what I can do, because of the small deformations and a linear constitutive relation or a linear relation between stress and strain, and for a small deformation, what I can say that the total deflection at C will comprise of two components. There will be a component of deflection at C due to first load, and there will be a component of deflection at C due to the second load. Okay. A similar equation we can write for deflection also. So what we can do, we can just ignore this Q load for some time. We just find what is the deflection using this Q load at C, and then suddenly we can forget for this point, and we can directly say that we can directly find the deflection of using this Q load at the point C, and then we can add them up. So this is a very simple way of doing it. Okay, so that is there. So now this is the way we use principle of superposition. Now you need to, as I told, you need to keep your mind two things: in which case you can apply, okay, the principle of superposition. You should remember always that, and then how to apply it. Now you can have a lot many problems in that, and lot many questions we can solve, but although they will be all same, their objective will be always same, the same type of theory or same type of concept will apply to come up with this answer. So anyway, I have chosen a problem. Okay, so a problem I have chosen like this. So what I am asking in this problem, to find the deflection of the following beam. So I am trying to find the deflection delta and the slope theta b at point B. So I am interested to find the deflection and slope at B, and this is my beam. So first of all, I have to ignore this, just focus this and check what was the deflection I was giving here. Okay, what was the deflection in theta due to this Q, and then replace this Q and check what is the deflection in theta due to this load P at this point, and this is a very classical problem. Okay, and then we can add them up. Okay, so let's solve this. So we can solve this problem. Let's see. So as we have done this problem a lot many times. Okay, so first we will do what? This A. Okay, now what we have? Yeah, so this is Q. So we already know that how this deflects. We know that. So we know that it first goes straight and then then it starts deflecting, and then it becomes straight. Sorry, like this. Like this, and from here a tangent will be drawn, something like this, which will be tangent at this point. Okay, I'll call it C. Okay, so we know that the short formula for the deflection. Okay, so WL power 4 upon 6CI, I think that is the formula. Correct me if I am wrong. Okay, so what I can do using UDL, so what did they deflection at B, Q 8 power 4 upon ATI. Just check if I am not wrong. I'm just trying to be sorry, C, not C, B, theta B. Oh, sorry, this will be C. Correct. This will be C itself here and also here, and it will be Q A cube upon 6CI. Okay. So we found that theta c due to first load, which is our first load. Second load is our now we need to find due to first load, not at this point, we need to find at this point. Okay, so we extend that. So as we have done this problem, we know that in this region the slope remains same, so theta c remains same. So we just, in this distance we add up this distance, that's all. Okay, so theta delta b will be actually q per 4 upon 8ei, sorry 8ei, yeah, 8ei plus the slope at this c point. We have found slope qa cube upon 6ei, and this is multiplied with the distance, so obviously the distance is b. Okay, it is b, so that is our theta b, and then theta's delta b, and theta b is same as theta c, that is q a cube upon 6ei. So that will remain same. Now for the case 2 or the load 2, the other load, we had a unit load, so we have direct results for that. So delta b will directly find. So we know that for it's a p load, so pl cube upon 3ei, that we know the deflection, and theta b is pl square upon 2ei. Okay, so now we know what is total theta c. Total theta c is qa cube upon 6ei plus qa cube upon pl square 2ei. That is the theta c, and both the loads are acting downwards, so they will be added up. Okay, they won't be subtracted. And deflection, I won't call it c, b, no, and delta b will be sum of these two, this one and this one. Will be q 8 power 4 upon 8ei plus qa cube into b upon 6ei. Okay, and plus pl cube upon 6ei. Oh sorry, that will be 3, not 6. 3ei. So this becomes the deflection. So we just found the deflection and the rotation at a point due to two multiple loads. Okay, so that's how we use the superposition principle. So you have to look at the problem before attempting it. So because it may happen that one problem could be more easier to solve in superposition principle rather than to solve it using integration. So my best advice will be, first you look at the problem, and you find out whether it can be broken into smaller problems or not. If a problem can be broken into smaller problems, then it may be a sign that it can be solved using superposition principle. Okay, otherwise if there is a normal problem, you can use that normal problem either using integration or fictitious load method to come up with this. So that is this there. Now that is there. So now we'll talk, we have done this, so we'll talk about little bit fictitious load method. Okay, so Okay, so what this method says that, so let's I'll explain with the problem. So suppose you have a beam something like this, and it is loaded something like this. This is suppose Q, and there is a point load also P. Okay, now it asks you, suppose it defines a point C, and this is distance A, and this is distance B. Okay, so now if suppose it asks you to find delta at C, okay, and theta as C. So one way we saw that we can use uh, the earlier method of superposition. So we can find, due to this Q load, or what is the deflection at this point due to this Q load alone on the beam, and then we can find the deflection in this point due to a load of Q in the beam, and then we can add them up. That is what we have done. Now another way to attempt this problem, to solve the problems using this method, was given, and they were what that another attempt was to introduce a fictitious fictitious how to introduce a fictitious load. So in the same beam I'll draw so this is the point C, this is A, this is B. So what I say, I draw what I do, suppose I need to find deflection. Now what matters is here what you need to find. So suppose I need to find deflection, what I'll do, I'll introduce a unit point load Q. Okay, I'll introduce a point load Q. Now using this, what I will do, I will write the strain energy. Okay, I'll write the strain energy. Okay, so it will be Q or something U, basically U will be strain energy. So strain energy due to bending we know is 0 to L m square dx upon 2 EI. Okay, this is the strain energy due to bending. So you know now all the formula of strain energy due to bending, strain energy due to torsion, strain energy due to initial loading, strain energy due to shear. Okay, you have already seen that. And as I was mentioning in the previous lecture 2 to 3 times, that professor will show you why we say that the shear is not important even though it is there. Okay, as I told, the beam bending theory or the Euler-Bernoulli beam theory, they were developed for the constant bending moment, that is shear force is 0. But however, all the problems which we solve, like this problem, does it have a zero force shear along the beam? No, it doesn't have. That means the beam bending theory can be used for those cases even where the bending moment and constitute the relation between bending moment and stress are not same. Okay, so we use there. So we saw in the lecture how professor found that how small is the deflection in a beam due to shear, and how large is the deflection in the beam is due to bending moment. So we can easily say that most of the shear in a beam is generated due to bending, sorry, most of the deflection in a beam is generated due to bending moment. Okay, so we can see, we can very easily ignore it this at this stage for shallow beams. There is something different happens when the beam depth starts increasing, and that is a very interesting other fact. Okay, so we don't need to go there. So what we do, we find the strain energy, and what will happen, this U, the U will be, it will be a function of what? It will be a function of Q. Okay, it will consist Q, a small q, it will be a function of capital Q, and it will be a function of capital P, and it will be a function of X. These quantities, it will be a function U. And then now to find the अब अगर now if you have found the value of u, which is the strain energy, which is a function of small q, capital P and small x. Now to find the deflection at a point, what we do, so we say that the delta is nothing but dou u by dou q, okay, dou u by dou q for q being 0. So what we'll do, we'll first derivate the u with respect to q and keeping all other quantities like small q, capital P, small x as constant, and then wherever q is remaining, we'll put it as 0. Then the answer will be the final answer, whatever we get. Okay. Now the thing is, as I just told, in the strain energy formulation, we can't use the superposition principle, and I hope you might have understood by now why we can't use, because the relationship between the strain energy and the bending moment is a non-linear relation. Okay, this relation is a non-linear relation, therefore we can't do a summation integral m square dx by e 2ei. No, we can't do that. It is not possible here because it's a square term. So you have to go to the bending moment, this m, and put this m appropriately. Okay, you have to put the m appropriately because it is inside the integration sign. Okay, so that is the concept behind the fictitious load method. So let's try to solve this problem. Okay, so what we'll do, so I need to find and name them A, B, C, D. Okay, now I want delta at B. Okay, so what I will do, or let's say another point, this point I mark this as L1 distance. This is L1 distance. Okay, so at distance what I need to do, first I need to introduce the fictitious load Q. Okay, now I write the bending equation. Okay, so I'll call this point as E. Okay, now my AB bending equation becomes how? So M becomes for this you need to find the, or I'll say with some other value, small q. Okay, because it will match otherwise. Yeah, so we will find the reactions first. So we get the reaction RA and RB. Okay, I'll just keep it as RA here because if I solve it, it will be more this thing, or I will write the equation for RA. RA into total is L. Okay, the total distance is L. RA into L is equals to P into A. Okay, so R is equals to P into A plus small q into L minus L1 plus capital Q into B, yeah, B. Okay, I think there should be P into A, not A, should be L minus A. Okay. Yeah, yeah. So this way we can find, we know all, so we can just divide and find RA. Okay, and from there, so M will be our what? It will be for this portion, it will be RA into L. RA into X for X greater than 0. So this is my origin. This is my origin. Okay, this is my origin. Okay. So for X greater than or equal to uh, A. Okay. Then M will be RA into, so some distance we'll write. So if suppose we are writing at this point, okay, at this point, so it will become X minus for RA it will be X and minus P into, I am writing that special brackets, X minus A. Okay, and this is for X greater than A equal to B. Okay. Okay, so now again we have to write the final M as for this portion. For this portion, so M is RA into X minus P X minus A plus Q into X minus L1. Okay, this is for X is between L1 no it will be this distance, it will be greater than so I have to define some distances. I'll define those. I will say this is E and this is F. Oh, I have defined the C. Oh, so only one I need to define. Yeah, C is been defined. So this will I will write in between, not like this. I will write here X being defined between A greater than X greater than this and should be less than or equal to A plus C minus E. Okay, in that region. And this one is defined X greater than A plus C minus E to A plus C. A plus C less than or equal to A plus C. Okay, and then we'll have one more final equation, for that will be the for last one will be RA into X minus P X minus A, and then this will be also minus, I think, minus Q X minus L1, and then the last one will be capital Q. So capital Q into A plus C. So capital Q will be L minus A minus C. Okay, or I would say X, not L. X minus A minus C. So this is for X belonging to this will be A plus C and less than or equal to L, total length. So this is m, and now we have to divide this whole integration. So I will write the u. What is u? U is nothing but integral, okay, 0 to L, we write like that, m square dx upon 2ei. Now what we need to do, we need to define for each new definition of m. So first definition is from 0 to a. So 0 to a, we have this as m, okay. So we'll take Ra into x. So it will become Ra square x square dx upon 2ei. Then the second one is from a to a plus c minus e. Okay, so from a to a plus c minus e, same this, but Ra will change, Ra into x minus p, Ra into x minus p x minus a, okay, and that to square of this into dx divided by 2ei plus third equation, we'll write this one, third one this one, and then fourth one this one, okay. So we will further write the other one here and the final form here, and then we can integrate it. As you can see, the Ra will not have a x term. You can see that Ra is just a function of p, L, A and L1, means there is no x involved in Ra. That means here in Ra square, there will be no x, only x will be involved in these squares, okay, in these squares, and you can integrate it very easily, okay, because it's in the numerator itself. So there will be nothing in denominator, x won't be in denominator, and we can easily integrate this. So finally we will have something, as I told, u as a function of our capital P, capital Q, small q, which is a fictitious load, and x something, no, x won't be there because we have integrated, L will be there, length, or some other defined length like small a, small b, those length will be there. So now what we need to do, we need to find deflection. For defining deflection, we will do what, we will say dou u by dou small q. Why small q? Because in our case this is the fictitious load Fl, okay. So I'll do with small q, and then I'll put small q wherever small q comes as 0, okay. So that is the way to find the deflection. Now question arises, what happens if we want to find the slope, okay. So for finding slope, suppose I have this beam with the UDL acting the UDL of value q, and I have been asked to find the slope at B. This whole length is L. Whole length is L, like this. I have been asked to find the deflection at Q, B, due to that Q UDL, okay. So what we need to do that, as you know, in case of deflection, what we did, we introduced a unit, a load Q, capital Q, and then we did what we did, we formulated the moment, we formulated the energy, and then we derivated that energy and we found. So here what we do, instead of finding putting a load like this, a unit load like this Q, we introduce a moment like some m, that is the moment, okay, that we introduce there. So let's solve this problem. So I'll introduce a moment here m, okay. Now let's see. So if we see the bending moment equation ours, so how our equation, so I will mark the points A, B and C, okay, this is B, this is A and C. Now if I write for BC, portion BC, what is the bending moment equation? M. So it is nothing but minus q x square by 2, simple. So that we know, okay. And then for, if I write for portion AB, if we write for that portion AB, so here you see the equation M is how it is q minus q x square by 2, and this minus m is also there, okay, it adds up to that. Okay, now I have to just check whether where I am considering my origin, okay, because origin is very important. So if this way and this way, so I am considering my origin here, this is 0 0 origin, okay. So whether I have written correctly or not, then we have to check. So BC means okay, so yeah, it will be L minus okay, I have to measure x from here, so yeah, it will be L minus x instead of x. We'll just change L minus x whole square by 2, okay, yeah. And in this case this is for BC, correct. And then for AB case okay, so I think the things will change if I put my this thing there. I have to define, I think, this distance L1 here, yeah, this distance is L1. So now moment we write for BC, not that way, this way. M is equals to, we have writing at this, okay, and our region is this much. So when we write the bending moment at this, what we write for this, we write Q into x minus L whole square by 2, okay. So here x varies from L1 to capital L, yeah. And yeah, and here, so at point L it will be 0, so I would say plus, I have to do plus minus q minus m, okay. And here m is, so if I put here x is equals to L, so you can see that the bending moment will become minus m, which is at point B. It should match with the condition, okay. And then for AB, this will be simply q into x square by 2 with minus, okay. AB means here, so x is varying between 0 to L 1, okay. Now let's write the u. So one will write 0 to L and one will be L1 to L. So here I will use this equation, AB portion equation will be used here. And oh, am I not audible? Am I not audible? So now I'm audible, I think, yeah. So I'll just go back again. So we had written the bending moment equation for both the portions, and now what we need to do, we need to just find our strain energy U, okay. So as you know, we have different equations for M, so bending moment. So or I will write to avoid confusion, MB, okay, MB, same symbol as professor is using, I will use MB. So here it will be MB square dx by 2EI, and here also it will be MB square dx by 2EI. Now here in the first one, in this case I will use this one AB, because this is 0 to L, which is what? 0 to L is this AB portion, 0 to L, L1, sorry. Okay, so this will be simply what? 0 to L1, then MB will be minus q x square by 2, that's whole square, dx upon 2ei. So this will be this plus integral L1 to L. Now here I will put this MB, the other one, this one I will insert here. Okay, so it will be minus q x minus L1 whole square by 2 minus m, that's whole square, okay, dx upon 2ei. Okay, now 1 upon 2ei I can take common. Okay, so that I can keep outside 1 upon 2ei because they are constant. Now we'll open the bracket, so this will become q square by 4. So I'll write q square by 4, minus sign will go away, so it will become just 0 to L1 x power 4 dx, correct, plus here it will be a complicated one because it involves two terms, so it will be q square by 4 x minus L1 whole square plus, I'll write the full integration right now, not 0, L1 to L, okay, like a bracket like this, plus m square and plus 2 into m q x minus L1 by 2. I am just opening this bracket using the identity a plus b whole square. Okay, so just that identity I am using. So if I use that, I am getting this as the answer, and then I do write dx. There is an integral because for whole. So this 2 gets cancelled. So let's further write it. So 1 upon 2ei q square by 4. This becomes, this is already understood. So it will be 1 by 5 into L1 to power 4. Okay, and plus, oh sorry, L1 to power 5, not 4, and plus this will be q square by 4 here, and if you see this bracket integration, we can directly integrate it. Okay, so we can say x minus L1 to the power 3, and we can divide by 3. Okay, like that. Okay, because it won't exist for any value of L less than L1. Okay, it won't exist, you know that it's a Macaulay bracket we call it. Okay, so this plus, for the other term it will be m square into integration if you do, so it will become x. Okay, so what I have missed here is the limits. I'll put limits L1 to L plus m square, it will be x L1 to L, and plus there will be m q by 2 because x minus L1 whole square, and this L1 to L. Okay, so let's open this or put the limits. So this will be q square by 20 L1 5 plus q square by 12. If you put L1 it will be 0, if you put L it will be L minus L1 whole cube upon, that's all, 3 we have already used, this plus m square, actually N minus L1, and plus mq by 2. If you put the L it will be 0, and there it will be L minus L1 whole square. Okay, this. Now what I need to do, I need to find theta. So theta will be nothing, dou u by dou m, as delta was what was delta? delta was, we used to write dou u by dou, suppose the fictitious load is q, so dou u by dou q. So here we will write dou u by dou m. Now you derivate, so because this doesn't have any m, I think, so what it will be? It will be 0, doesn't have any m. Here there is no m, only m exists here and here, okay, and that too m tend to 0 we have to say, okay. But let's first find the derivative of dou u by dou m, and then we'll put 0. So this will come out to be 2m L minus L1, and here it will be q by 2 L minus L1 whole square, okay, and 1 upon 2 is there. Just let me see I have done this correctly or not. I think I have missed something. Yeah, I have missed a square here. See, there was a square. I'll show you. This square should come here. That's how this will be formed. Or as I told you, it will be a square here also, because this is a square, so it will be 4 here. I'll correct it. I missed it. Sorry. It will be 4 here. Okay, because it's a square, and m will be a square. I am just using identity a plus b whole square. So it will be q square by 4, this q square by 4 into x minus L1 power 4. This will be plus m1 square plus 2 into m into this expression. So that is q into x minus L1 whole square by 2. So 2ab. Okay, and now I will incorporate that here also. So it will be power 5 here, instead of that it will be power 5 here, and instead of 3 here it will be 5 here. Okay, now the change will be here, so it will be cube here, sorry, it will be cube here, instead of 2 it will be 3 here. Okay, so finally it will be cube here, and instead of that it will be 3. That also I will change. It will be 5 here, and it will be 20 there. I hope you are getting this thing. Okay, so yeah, so now this will be what, cube here. Okay, and this was 3. Yeah, 3. So here it will be 3. Okay, because I am just derivating this. So now you insert, now you substitute m as 0. So this goes to 0, and it becomes q by 3, and this 3 multiplied with the 2ei, 6ei, and L minus L1 cube. So that is theta. Theta becomes this. Sorry. Okay, theta becomes this, q by 6ei L minus L1 whole cube. Okay, so we are asking at this point. So that's how we find the deflection. Sorry, in this case we are finding rotation. So what I am trying to tell you, if you want to find the rotation also, you can find with this using the same formulation, the rotation also. Just you need to introduce a moment, fictitious moment, and you have to write the bending moment equation for each portion, and then we can solve it to get the answer. Okay, similar way we use for the load also. Okay, in a similar manner. Okay, so that's what because there is not much in these two methods. Why? Because they are same repetitive methods. However, you can change the problem in a way you want. Okay, so instead of going to various problems, but they are having same way, I have just taken these two problems, which will be able to fairly cover the concepts. Because what could be asked, that one more thing, that the rotation also can be asked. Okay, so rotation is also very like easy way to solve using this. Okay, now there was some doubt from, I think, Arjun. I'll take up that doubt. So can you explain that question, Arjun? Okay. 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 Yes. The free end is again supported by a, so something like this. Huh. Okay. Yeah. Okay. Okay. Huh. Yeah. So is it like something below? Extend on both ends. Okay. Okay. Oh, okay. Okay. Okay, I'll draw like this only. Okay. You have something there, and length is 10 meter for both. Hmm. Yeah. Okay. Okay. Anything else? Okay. Okay. This. Hmm. Yeah. 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 Yes. Yeah. 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 Yes. 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 Yeah. Okay, so you want the force. So RB will be 3 by 8 into Q is given as 2.5 into L is 10. So it will be uh, so you just find this quantity 75 by 8, 9.37, correct, kilonewton. Okay, no issue. Right now we'll use 9.375. Okay. So now this 9.375 kilonewton load will act at this point, and it will act how? It will act upwards. Yeah. Huh. Okay. 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 So you're saying for this reaction range 8.38 to 9.24. Okay. Okay. You have raised this with the TA team, no? Okay. Have they replied? Ah, no issue. Then wait. You wait for them. I don't think there is a issue here. Okay. As far as the concept, as you have told me, the concept seems to be fine. Okay. And I believe in this case, this beam will be perpendicular to this beam actually. Okay. So like in if you will, yeah, perpendicular, because it will go something like this, so it will be supported here. So suppose this will go like this, so here it is fixed and it will be supported here as a roller, correct. So that load will get transferred. This is how you connect the beams, as I have told some class or lecture back, because we have something called primary beam and secondary beam. So what happens, secondary beam comes and rests over primary beam. Okay. So I think if you have raised, I think they will see to it. I don't feel there is any problem with that. It seems fairly fine. Okay. Yeah. Yeah. 9.24, any if I say that this is the correct answer, then 9.24 can't be the highest limit. It should be 9 like 39 something. That will should be the highest limit if this is the correct answer. Yeah. This is very pretty simple because professor also has explained this in class, and he has done the this problem in the lecture itself. Yeah. Yeah, could have. That's what I'm saying. It could have been on the part of the NPTEL team, that, or somewhere it could have been the figures would have been misplaced from here to there. I would say let you wait and let's see what the reply the TA team. Okay. Okay. Ah. Okay. Yeah. Okay. Yeah. Yes. Yes. What do you use W? Yeah. And what is L? Yes. Did you use I for as this? Okay. Did you convert E properly? MM. Okay. Yeah. Oh. Yeah, yeah. Yeah, yeah, yeah. Yeah, yeah. Okay, okay, okay. Yeah. Yeah. Okay. Okay. Uh-huh. Okay. 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 Then it should be half on both sides. Hmm. Hmm. And what is okay for one end? It is going 4.6. So what they are giving? What is the answer for the other end? Yeah, means they are only asking this end. They are not asking this end. Okay, this one only. Okay, they ask this also? QL minus 3 QL by 8. It is 5 QL by 8. 5 by 8 into 5 into 10. So it will be 125 by 8. What it is coming? 125 by 8? Okay. Good, good. That means you are following correctly, then could happen. That's what I am saying. Maybe the while inserting the correct answers, the figure could have been, the digits could have been gone here or there somewhere. It's could be so that yeah, 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 yeah. Big, big range. Hmm. Yeah, 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 yeah. Yeah, it's fine. I think they will reply to that. I believe. Okay, because that comes into their jurisdiction, their preview. So they will do that. If there really any issue with the ranges, they'll reply appropriately, as has been done before. Also, that's what I'm saying. Maybe could happen due to like digits going from here to there. Okay, it's very small. This thing because yeah. Oh, okay, 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 okay. Yeah. Okay, okay. Good, good. That's good. See, sometimes learning comes in this way also. It's not only one way. Let's see. So those things we get to know when we go about behind a thing and we think and think. So that's also a part of learning. So yeah, it's very important actually. So it gives a different perspective when we look ourselves. It's like a review of ourselves only. So yeah, that's also a part of learning, and this gives us more confidence. No, that okay, we were correct in our approach. Yeah. So as you have seen, you have found the last part very correctly, which is matching with the your answer also and the range also. So that means it can never be possible that it's not a magic that you turned up with the correct answer in the last part and you have done wrong in the rest part. That means there is some other issue has been there, but you have been correct in your concepts. So that's more important. Yeah. Yeah, maybe that's all. That's all. It's all about range only. It's all. That's why I said the digits have been gone there and there somewhere. Some 9 has been made 6 or something like that. Yeah. So like yeah. So that is been done to like actually. Uh, uh, the thing is, there are different aspect to it actually. So we can have a little bit higher range with respect to the reactions. Okay, but and it has a practical aspect. So what happens if we go in an industry, the range for error in the deflection is always very less. It is always kept very less. You can't go means in very specific industries related to machining specifically. You can't go the means the complex or the more importance the machine would have its value, the more rigorous range of error will be there, 0.01% or 0.1%. Maybe in civil construction you can come till 2 or 3% error in deflection, but you can't go even max to max you can go 5%, but you can't go above that. But a different application requires different. So I think the narrower range in deflection has a practical aspect to it, that it shows actually that in the industry or in any problem the narrower range is required in deflection. Yeah, because deflection is more, you can say, uh, in most of these structures deflection plays a more important role. Okay, because whenever we design for a strength, we most of the time design it over strength. So if suppose a support is carrying some 15.53 kilonewton of load, so if that is being changed to 15.59 or 15.9 also, it will take that load. Even 16.9 also it will take, because most of the time we design higher for strength, we give for a over strength, but deflection is more important to handle. And because this is one way, and because it has it changes the geometry. If deflection becomes higher than the allowable, it will change the geometry. You understand my point? So if we in our analysis what we are doing, all we are saying beam, we are showing how we are showing the beam by a straight line. As you can see, all we have shown in them by a straight line. So what happens if the deflection criteria is not met? It will be not a straight line, it will become a curved like this. And as soon as it becomes curved, it doesn't serve our purpose. So that, I think that is the reason. But yeah, as you have found correct answer in the fourth part, I believe there would be a issue with the range, and that will be fixed, I think. Yeah, it will be fixed. Yeah. 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 So any other question by anyone else? Okay. Okay. Yeah, yeah. What is your question? Just let me know. What is your question? Ah, yeah. Yeah. This was part of week 11. Okay. Okay. Yeah. 2024. Okay. Aluminum alloy. Okay. Young's modulus is 270, 70 GP only now. And what was other? Mu is 0.3. Okay. Yield strain was 0.5%. That means 0.005 micrometer per meter. Okay. Hmm. Hmm. Okay. 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 Uniaxial tensile strength. Okay. 500. Okay. This is strength written. Okay. Okay. Ah, okay, 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 okay. It's a solid shaft. Okay, okay. Yield strength. Okay. I think that is fairly straight. Sigma y is epsilon y times E. Correct. 0.005 into E. That's all. Okay. Okay. Yeah. Oh, 350, not 315. Okay. Okay. Major principal stresses. Stress. Okay. 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 How you found the axial stress? Okay. 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 Hmm. 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 Yes. Okay. 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 Hmm. But that was written for a Cartesian coordinate, no? We are living in a polar coordinate. So what way I would say, you have to first write the sigma matrix. Sigma theta theta, sigma r theta, or even for sigma rr, not theta theta. Sigma rr, sigma r theta, sigma rz, then sigma theta r, sigma theta theta, sigma theta z, and sigma z r, sigma z theta, and sigma z z. Now you have to identify which all are 0 and which all are not. Okay. So when you apply a uniaxial load like this, there won't be any stress developed in this direction. So you don't have any sigma r. This goes to 0. Now you are having shear on the surface. Okay. If I draw the cross section, so this will be something like this. So you are having shear like this, correct? Yeah. So here this direction is what? R. This tangent is what? Theta. Okay. This is the r theta plane, no? So obviously this will be r theta shear, not rz. It's a plane. On this plane it is a r theta plane. So this tau will come here and here. Okay, they are same, no, because it will be symmetric. We have seen that, correct? Sigma matrix will be symmetric. Now what remains? Okay, theta theta. So we don't have any theta theta here. It's not there, so theta theta won't be there. And we have what? R. Okay, first look at RZ. So if I look at RZ, so RZ will be, yeah, we have to find an RZ plane first of all, no? So yeah, so what is what? This is Z direction, and if I cut a plane like this, that was a, this plane was a sigma, r theta plane. This was a r theta plane. So if I cut like this in a longitudinal direction, it will be a r theta rz plane. So some rectangular portion will come something like this, and we will have this direction as z and this direction as r. Okay. So yeah, so that will be also 0. We don't have any rz. Okay, we have only twisting on the surface, no? Even the twisting which is happening here also, we know that it varies, but it will all, this varies like this, but it varies on r on theta, r theta plane. Okay. Now, so this will be when 0. sigma zz will be there, which we found, and z theta and these terms will be also 0. So now you found which will be there, this and this will be there. Now you have to apply what? You have to apply the so something. I will populate the matrix. So it will be here 0 0, no, not 0, that will be tau r theta 0, tau r theta 0 0 0 0 sigma zz, correct. Now you do that what we used to do. What we used to do to find the eigenvalues, we used to have the eigenvalue problem. So what we will do, we will sigma minus lambda identity is equals to 0, correct. No, I didn't get what happened. Oh, okay. Sorry. Thanks for reminding. Okay. Just a minute. Am I audible? Okay. Yeah. So here what we used to find this was our eigenvalue problem, no? We have done this. Maybe that way we are solving, maybe it is coming incorrect. Okay. So that sigma 1 comma sigma 2, what I am saying, maybe this formula, because this formula is for, we usually use for plane stress, sorry. Okay. This one we use. So like, I am not saying it won't work, it may work also, but better is to always go with this one. Okay, because this is like fail safe, it will never fail, it's not even it will never fail, what I am trying to say. So we have our matrices. So what we can find determinant of lambda. So this will be minus lambda and tau r theta 0, tau r theta minus lambda 0 0 0 sigma zz minus lambda. Determinant of this should be 0. So we will find an equation in lambda cube terms. Okay. So we can open about this, even it is not that difficult here. So it will become sigma zz minus lambda, and it will be lambda square minus tau r theta whole square. Okay. So I think that formula can be applied also here. So one lambda will be sigma zz, another lambda will be plus minus tau r theta. So is it not matching with yours, or something is happening? Okay. 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 Yes. You formulated quadratic equation in this form? No, this one, sigma 1 and sigma 2, na? Okay. So one, I will just ask something. What is this value of sigma zz, this thing, this value? What is the value sigma zz? 21, Excel, 21.2 megapascal. I think it will be more, no? Okay. 15 into 10 to the power 3. Yeah. Ah, okay, okay, then fine. Yeah, yeah, yeah. Correct. Ah, correct. And what is tau r theta? 189. Okay. Hmm. Okay. Okay, okay. Okay. So the answers you got, which you said around 210 or something, those are correct, matching with the this thing. Okay. 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 Ah. 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 Okay. Which is in week 12. Okay. 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 Ah. Ah. Hmm. MT by pi d cube. Yeah. Hmm. Hmm. Yeah. Yeah. Hmm. 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 Okay. Okay. Torsion. There it is bending and torsion. Hmm. Yeah. 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 Okay. 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 Yeah. Yeah, so for bending and it will be in a different way. But yeah, you have to just remember the system. If you are using a Cartesian, then both Cartesian you use for torsion and bending. The thing is, one is being derived in Cartesian and one is being derived in uh, polar coordinate, so that makes a little bit problematic. That's all. Yeah. Yeah. Yeah, so that yeah, that I'm also like thinking why it is coming in this way and it is being shown correct in that way. So just tell me what was the value of the sigma 1 which you got? 200 MPa, and that is also matching there. Sigma 2 was 0 and sigma 3 was minus 178.7. Okay. 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 Hmm. Hmm. Yeah. Okay. Yeah. Yeah. Here using these. Hmm. Yes, yes. Okay, okay. Hmm. Yeah, okay, yeah, yes. Hmm. Okay, okay, okay. Hmm. Hmm. Okay. Ah. There is a 1 by 6 also, no? 1 by 6 in whole. 1 by 6 of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma. Yeah. This is not 1 by 6? Okay. 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 Hmm. Yeah. Hmm. Hmm. Okay. Hmm. Hmm. Okay. 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 I understand. Understood. Correct. Correct. Hmm. So in third, in the last part when you did put the value of sigma 1 minus sigma 2 means all the three principal stresses. So whether it was satisfying the 1 by 6 criteria or not? Okay. Okay. 2 times the square of the yield. Hmm. Yeah. 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 You took the care, take care of the signs. Hmm. 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 Yeah. Okay. Hmm. 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 How factor of safety is defined? Hmm. Means you are saying right hand side divided by left hand side. No, that's what we have to see how the factor of safety is defined. If factor of safety is defined like right hand side divided by left hand side, then it is fine. But if it is not, then usually it is defined like that. Usually it is defined like that. Yeah. Hmm. Okay. Yeah. Hmm. 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 Okay, just last part you read. What is written? Question you read. Hmm. Hmm. Okay. Hmm. 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 Yeah. Hmm. 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 Okay, do one thing, do one thing. Wait. What value you got? The factor of safety in the last part, what you got value? 1.14. Just do one thing, you take a square root of that. Is it coming in the range? Yeah, so you can't take a ratio of squares. Factor of safety is actually the ratio of sigmas. So you have to take the ratio of sigmas, not the squares. Okay. Yeah, yeah. Yeah, because here the yield criteria is defined as the squares. In Tresca, it is not like that. It is sigma max minus sigma min divided by 2 less than equal to tau max or tau like that. Tau max is equals to tau max is less than equal to sigma y by 2. So there it is simple ratio because but you always factor of safety is the ratio of the stresses, not the square of the stresses. Okay. Yeah. Okay. Okay. Yeah. 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 Yeah, so see, actually, when we have to come to a design stress, like right now, what you are doing, you are finding the factor of safety. Okay, but in case of design, always the factor of safety is given. It is not a way to find it. Okay, so suppose for a particular part or some crankshaft or something, the factor of safety is defined as 4. So what you will do, you have the for that material, you know the yield stress. Okay, So you find that for, if suppose you are saying the material which you are using for crankshaft satisfies the von Mises criteria. Okay. So what you will say, okay, so my right hand side is root 2, because there was 2 sigma y square. So I will say root 2 into sigma y. Okay. So root 2 into sigma y will be the value, that is the permissible value of stress. I will divide it by the factor of safety of 4. Whatever value is I got, that is my design stress. Now my stress in my each part should not be above that value. That I have to ensure. That should be in my analysis. Yeah. So in von Mises criteria, how you wrote the criteria or the yield function, it was sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square should be less than equal to 2 times sigma y yield square. Correct. So basically the von Mises stress on the left side is actually the square root of that quantity, sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3. So analogously on the right side, the value which is the allowable value would be square root of 2 into sigma y whole square, which will be square root of 2 into sigma y. So when you divide that quantity with factor of safety of 4 or some value, you get the design stress. Exactly. For finding the factor of safety, you have to go with the square root. Yeah. 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 Okay. Okay. So we'll close for it today. Okay. We'll then meet tomorrow. Okay. Okay. We'll close it for today. Yeah. Thank you. Thank you. Thank you very much. Thank you. Bye. 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 Good night. Bye.